Uh, Good morning, all. Welcome to this video. Today, my name is Rahul Kumar, and I'm a PhD student at University of Tennessee at Chattanooga. And today, I'll be talking about MPI, that is Message Passing Interface. And today, I will be implementing matrix multiplication in MPI. So, a quick overview. I'm making this video as a requirement for one of the project under the course Introduction to Parallel Algorithms. So the topic is MPI matrix multiplication, and in this basically we are considering two matrices. Let's go over here. I have a slide. Yeah, it's over here. So we have two matrix, matrix A and matrix B, and we are using multiple processes to parallelize this multiplication on multiple processes. So how it works and what is MPI, that will be the focus of the study and focus of this video. And we'll be talking about different communication techniques that are available in MPI and how they are different from each other and which one is more faster compared to others. So the three communication types that we'll be discussing are blocking point-to-point, collective, and non-blocking point-to-point. And then there is some analysis on that. So let's come here. We'll go through MPI first. Okay, yeah. So what is MPI? So MPI is a standardized and portable communication protocol used for program parallel applications. So that is, it can be used on distributed memory systems such as cluster or even in your CPU where you have multiple processors. So, and supercomputers and multiple node systems. And it's a little bit different from the thread-based parallelism in which like in OpenMP you create a master thread which then forks out multiple threads whenever there is a parallel section, and MPI is much more involved, so you have to explicitly create a parallel section, whereas in OpenMP and other uh, parallelizing techniques there are certain pragmas that you can use and it will automatically create a parallel section in your code. So, what MPI does is like you have multiple processors and each of these processors have their own memory. So MPI serves as an interface for exchanging the for communication between multiple processors. So why do we need, like I told before, each processor has its own private memory and so they cannot directly communicate between each other. So it's a explicit message-based approach in which enables two processors to talk to each other to communicate, which is essential in parallel computing. So how it works is it provides you a distributed work, data efficiency, like and synchronization. Like there are multiple subroutines that you can use to synchronize to distribute data and many more operations. So yes. So when a MPI program runs, it launches independent processes and which communicates through this particular interface. And yeah, so this is the pragma that you used for communication. It's MPI convol. So it it helps all the processes in your code to communicate with each other. And in MPI, a rank zero processor act as a master and others will serve as a worker. So what I mean is that if you are scattering or distributing data among multiple processes, it will be done through rank zero processor. And similarly, if you are gathering data from multiple processors, it will happen from this. So to enable your C program to run with MPI, you have to include this particular library MPI.h, and to initialize any MPI written inside your code, we used this particular subroutine MPI initialize. So let's go further. Yeah, why we need MPI is, I think I have covered that bit. Each processor has its own memory and they need to communicate with each other. And one of the efficient ways is MPI. And one of the advantage with MPI is it's scalable. So because you have distributed memory system, so you can integrate multiple number of processors on that. Okay, so the problem at hand is we have two matrices. One has n rows and k columns, and the other one has k rows and n columns. And this we are doing this multiplication matrix multiplication uh, using MPI. So that is we are creating parallel. We are creating multiple processes which will that will take on some portion of all this multiplication. So how it works is we provide a copy to each processor because how matrix multiplication works is you multiply first row with the first column, and that gives you one element over here. And similarly it goes on. So you cannot distribute both of these. You can only parallelize one part of this matrix. It's so this basically creates a bottleneck because you cannot distribute this, but that is the problem at hand. So like this, we reduce this n cross k matrix into a single uh, column matrix, and then we distribute uh, the data points among multiple processors. And each processor has a copy of your matrix P. So using doing some matrix manipulation, we can easily calculate the product. And you can see that why communication is needed, because it may happen like uh, then it may not be the case that you are giving a complete one row to a particular processor. It may be half of the row or maybe more than one row. So a communication between these two become essential because the other processor has to know that all these values are taken care by the by some other processor. So and then you have to sum all these because when you multiply A11 B1 then plus A12 B21, it works like this. So you need so if you take that A1K is not a part of processor 1. So this particular A1K into BK1 will be taken care by some other processor, and then you need to sum it with the other elements of that particular row to get a particular element in matrix C. So the communication is necessary over here. If you have a matrix C, so your C11 will have some of these and these over here. And if you say that this is not a part of processor 1, then this multiplication will be taken care by some other processor. And then the communication is required between the processors. Yeah, so the first communication that we are implementing is blocking point to point. So in this, we use subroutines such as MPI send and MPI receive to communicate between processors. So like this, you can see that a processor has a main area in which the operations are run, and there is a buffer zone. So any send signal will first go to the buffer zone, and when the processor is free, then it will pass on to the processor application. So what blocking means is that the sender waits until the message is delivered from its buffer. So this processor will wait until this buffer zone provides him the message. So this basically creates latency, and this results in communication lag. And similarly, the receiver wait until the data arrives. So in this, computation and communication cannot overlap. So if the processor is busy with the computation, it cannot communicate with other processors. And this is one of the disadvantages of this particular communication. So the process sits idle during communication, and it's considered one of the slowest method if the data is too large, which we'll see from the results. So where it fits is in, so how it does is master process, like that is the process zero. It slices the matrix A among different workers, and then the workers must wait until the data arrives before computing. And master also waits to receive the results. The second method is collective communication. In this, we use these subroutines, MPI broadcast, that is broadcasting some data to all the nodes. Like in our case, we are broadcasting a matrix P to all the nodes. And MPI scatter, that is scattering some portion of the data among nodes. That is, we are dividing matrix A among multiple processes. So in that, we'll be using this particular subroutine. And then the other one is MPI gather, which gathers all the data from multiple processes. And then we have MPI reduce. So in this, the communication happens internally, and the processor participate together in the group communication method. Like at once, all the processes are communicating with each other. So it's faster. The code is less code to write, good for regular structured problems. Like, okay, let's see the disadvantages. Less flexible. So the flexibility is less because all the nodes are communicating at one time, and it may result in some latency. Yeah, so this is what I was talking about. Mm. So yeah, so in each of these we need to provide certain inputs. So the first input is the data that is needed to broadcast, the number of elements it has, data type it's an integer or a float, then the processor which is taking care of the communication, that is read root processor. So this value will be 0, and MPI communication. Similarly, in scatter, you have input data, number of elements, data type, output buffer for each processor, number of elements, and then the data type, that is that the data type that you receive, and the root will be 0. And similarly for gather and reduce, you have these particular inputs which can be easily found on internet. So the next one is non-blocking. So in this, basically your communication and computation overlap. So it's kind of a pipeline system, pipeline kind of architecture. So how it happens is you use MPI send and MPI receive. So in this, communication starts, but your processor no need does not need to wait for it to function to finish. And then one of the things in this is that you can use MPI wait and MPI test to check whether all the processes are at same level. So like all the processors have done their uh, computation before you uh, reduce the data. So it has good performance compared to the blocking and collective one. And one of the challenges in this is like you need to explicitly code everything, and it's a little bit more involved as compared to the other two communication. So let's go to the coding part. Yeah, so this is point-to-point communication. So in each one, I'm comparing it with a serial run to check whether the results are matching or not. And the number of elements is 100 rows and 32 columns. And this is your basic matrix multiplication in which you're reducing A into a simple uh, row matrix, and then you're multiplying your grade. You're basically calculating the matrix C by multiplying both of these. Then there is a function called is equal, which checks whether if your A and B matrix are same. So if any of the element is not same, then it will return zero. It basically takes care that your both of your matrices are not identical. There is some difference. And then this is the main function in which first you are initializing your MPI, and then you are defining the rank and size of your MPI. But then matrices are created. This is how you distribute the rows. So you have n number of rows, and the size is the number of processors it has. So you divide the number of the number of rows among multiple processors, and sometimes it may happen like uh, it's not a perfect divisor. So based on that, you distribute more. The remainder one are explicitly distributed among other processors. So you can see the local row, it was row per processor, plus if your rank of the processor is 0 and remainder is 3, so it will get one row unless all the rows are finished. So when the rank is 4, the processors after that will not get any more rows. So this is the memory allocation you are creating to matrices A and C with memory local rows. These are local matrices because A and C will be of same size. And then you're creating allocating memory to matrix P. So in here you are using the processor 0 to populate the values in your matrices. So we are using random number generator for doing that. So A and B are created. And then you're doing a serial multiplication is carried over here, and then we are using MPI time to calculate the time that it took for the serial computation. So the next one is broadcasting. So here, because matrix B, a copy of matrix B is stored on each of the processors, so we are broadcasting here. It's B, the size of the matrices. The type is float, communicator is 0, and you are communicating among all the matrices. The next one is it synchronizes before parallel time starts. So you make sure that all the processors are at same level. Then this is distribution for matrix A. So you're sending rows, which we already calculated on the top. So you're sending these rows. This is this particular thing, then this is the size, float, I, then 0 is the rank, and MPI communication mode. Let me see what is I over here. Yes, and maybe I have to check it once. Okay, so you have a buffer, count, data type, and this is destination. So destination is on which processor you are running. So it specifies that, yeah, so over here you can see that if it's less than size, so this particular part of the matrix is sent to your processor I, and then that creates the tickets of that particular computation. So then similarly you have for receive, where you're receiving from each mm, from each processor. So these are initially, I think these are stored in zero. Yes. And this is serial communication. Okay, so then you are using gather to receive. So you're gathering results and using MPI receive, and it is stored in that particular processor. The next one is barrier. You're creating a barrier so that all the processors are at the same level before you end your program. So then it's comparing the timings, and then you're checking whether A and B, like the matrix which is being calculated is same from serial and your MPI, your parallel computation, and we are then freeing up memory, and you end the MPI section with MPI finalize. So this is MPI P2P. Let's go over collective one. Yeah. So the major change will be how the communication and distribution is taking place. So all these things are similar. Yes. So here you have send counts, receive counts, and displace. Okay, this is the displacement. Yeah, so over here you are allocating the memory to different matrices, and then yeah, it's serial. Yes, over here you're this is the section that is different. So you are broadcasting B that is similar, and here you use scatter to distribute matrix A over different processes. The other part will be similar. Let's see the third one, that is non-blocking P2P. Yeah, so in here, so you're creating variables local row and start row for each processor because they are because in this one you no need for the communication for because communication and computation happens uh, simultaneously. So you need to specify the start and end row because in this one we are not explicitly uh, waiting for the communication to end before uh, we are not waiting for the processor to finish before giving another task. So in this explicitly we need to mention the number of rows and this uh, the index at which it is started. So MPI broadcasting, it's similar. Yes, in this you are using MPI request, send, and receive. So over here, if we see MPI receive, so from here you're sending the number of rows, float, processor, and your rank 0. And if one of the processors have already done the computation, then you have provided a receive also, and otherwise it will wait for it to finish. So then you're requesting for matrix C, and then over over here it waits for the processor to reply. So let's and similarly you're freeing up the memory allocation and finalizing the endpoint. Let's go a little bit on the results. So to compile this, it's very simple. Like if you have this code named this, you can use directly MPI run or MPI CC to compile it, and it will run. Uh, okay, so maybe I have to use MPI CC. Yeah, so it compiles, so it will work with MPI CC. Yeah. So it throws some of the warnings which I checked is these are not relevant. So let's ignore these, and then you can see over here the sequential one and the non-blocking one. Timings looks much similar because right now the metric size is very small, so the communication latency uh, will make it very close to the sequential run timing. So in the results I've compiled with multiple metric size. Let's see over here. This is with 1,000 rows and you have 32 columns. So you can see over here like your non-blocking one, yeah, over here. So it performs a little bit better compared to blocking and collective one. And you have more time in collective communication. So here you can see if you have 20,000 elements, the timings are a little better for non-blocking P2P, whereas it's larger for blocking P2P, which was what the theory predicts. Like blocking P2P has the highest one, then MPI collective is a little better, and MPI non-blocking will be more better, more faster compared to all these three. So this agrees with the theoretical part. Still, the numbers are not that good, but I think these will improve if once you go your data size increases and you have much more complex problems. So non-blocking B2B will be performing better. Okay, so thank you all for watching this video and have a good day.